In this lesson, we're going to consider some basic facts about normal distributions. To begin with, we need a good definition. So our definition of a normal distribution is here, and we're going to fill in a couple of blanks for this. If a random variable has a probability distribution whose graph is continuous, bell-shaped, and symmetric, it's got to have those three features, then it's called a normal distribution. Everything that we looked at in Chapter 5 dealt with discrete probability distributions. Now we're going to look at continuous probability distributions. So this is a normal distribution. And the graph is called the normal distribution curve. Now, there's a complicated looking equation for that, and that's here on the slide. It's also found in your book. But what I'd like for you to notice about this is that in the equation, E is actually a numerical value. It's an irrational number, just like pi is an irrational number. And we've used pi in other classes, I'm sure. And that these are two approximations. And so the population mean and the population standard deviation, those would be given. And if you replaced everything with those numbers, then what you have left is this x here. So you've got y expressed in terms of x. So anyway, what I'd like you to get out of this equation here is that the shape and position of the normal distribution curve depends on the parameters. And the parameters are these two things here, the population mean and the population standard deviation. So we're going to fill in the blanks with that. They're based on or depend on the parameters, which are the mean and standard deviation. Now, I've got this little PowerPoint on the main page in our website. So if you want to take a moment and print that off, and then you could take your notes right on the PowerPoint. It's just up to you. So it looks a little cleaner on the next slide. Then another fact we need to consider is when we consider a normal distribution curve, what it looks like is this bell shape that we have here. And in this first drawing, we've got a red curve and a blue curve. Well, they're both bell-shaped. They're both symmetric about the mean. Those features that we have for the normal distribution, they're both continuous. The one thing that's the same is both of them have a mean of 0. What's different is the blue one has a standard deviation of 2, whereas the red one has a standard deviation of 1. So I'd like you to notice with the red one having a standard deviation of 1, it's not as spread out as the blue one is. The blue one is kind of like you took the red one and pulled on the two tails to get the blue graph. In the second little example here, these two curves have exactly the same shape. It's like you picked up this one that's in blue and marched it to the right, and now you got the curve in red. So the standard deviations stayed the same here in this one. Notice that they're both 2, but the means are different. In the blue one, the mean is 0, but in the red one here, the mean is 2. So to fill in our blanks, when the population means are the same, that's going back up to the first graph, but the population standard deviations are different, the curve with the larger population standard deviation is more, and we're going to fill it in with something fairly simple here. I'm just going to say it's more spread out. Because remember, standard deviation measures the spread of the distribution. And when the population standard deviations are the same, the spreads are the same, but the means are different, means measure center, then the curves have the same shape, because the standard deviations are the same. So they have the same shape, but they're centered at different points along the x-axis. And here again, the next slide spells that out a little cleaner. The summary of the properties of this theoretical normal distribution. So we've got a list of properties here we're going to fill in. The first one being up here at the top, the normal distribution curve is bell-shaped. And then the second fact is the measures of center are those three measures that we looked at in a previous chapter: the mean, the median, and the mode. And since this is bell-shaped, it only has one peak. So there's one mode, one place where you have the most values occurring. The normal distribution curve is symmetric about the mean. If you were to, pick your paper up and fold it along that mean, you'd have exactly the same thing on the left as you do on the right. The normal distribution curve is continuous. When you draw it, you just put your pencil down and draw the sketch, and you don't have any gaps or holes or stops. This is a nice smooth curve. The curve approaches, but never, got that wrong on the slide. Let's fix that. But does not. It approaches but does not meet the x-axis. So it gets closer and closer and closer to the x-axis, but it never touches it. The total area under a normal distribution curve is equal to 1. The area under the part of the normal distribution that lies within 1 standard deviation is 68%. And we've mentioned this earlier. It's called the empirical rule. 2 standard deviations of the mean is approximately 95. And within 3 standard deviations, we've got 99.7%. Almost all of our data within 3 standard deviations. And this next slide is much better looking if you're taking notes from the slides. Okay. To identify a distribution as symmetric or skewed, because the normal is symmetric, so we need to fill in that first blank with that. The normal distribution is symmetric. And that just means the data is evenly distributed about the mean. If you have a situation where the majority of the data is to the right of the mean, that means, like in this case, we've got most of our data here to the right side of the mean. If that happens, the tail trails off to the left, so we say that's left skewed. Well, another name for that, as well as left skewed, is negatively skewed. It's left skewed, it's also negatively skewed. And if the majority of the data is to the left of the mean, here's our mean, so we're looking at most of the data is on the left-hand side, like in this sketch, then that means this is skewed right or positively skewed. So the tail of the curve always indicates the direction of the skewedness. Okay, and we've talked about that a little bit before. Now, with this standard normal distribution, it's special. We've got the word standard attached to this. So it starts off as a normal distribution. But what makes it standard is the mean and standard deviation. So the mean of this distribution is 0 and the standard deviation is 1. So as you can tell here from this curve, this is the center here at 0, and this is 1 standard deviation to the right, 1 standard deviation to the left, and we've talked about that a little bit before in the past. So all normally distributed variables can be transformed into the standard normal variable. By standardizing the score or standardizing the value. And the way we do that is a formula that we're already familiar with, where we find the z-score. So the z-score is actually a description of the number of standard deviations that a particular value is from the mean. Standard deviations that a particular x value is from the mean. And we're going to be using that with our standard normal distribution. So we're taking this normal curve and standardizing it by using this little formula that we've had in the past, getting a z-score. So that's a little bit cleaner look on our PowerPoint. Okay, now that's the basic information. In our next video, we're going to look at how we can compute this for different values.